We are moving on to chapter 2, and we are going to start talking about functions. This is really getting into the real part of this, that is the STEM college algebra. Everything before this is really mostly just review. Okay, so we have talked about a little bit of these things here and there, but a relation is a set of ordered pairs. Well, it could also be a set of ordered triplets or something like that, but basically it's taking a set of components or numbers that are part of your domain, and we want to see how they relate to another set of components that we call our range. So for us, we're just going to deal with two variables, so we only have the domain and range to worry about. We want to find the domain and range of this following relation. So remember, these are ordered pairs that are representing an X and a Y. And this is just another X and another Y. And this is just another X and another Y. But it's telling me that there is a relation between these X's and Y's. Somehow this 0 is related to this 187. 2 is related to 225. Whatever it is that's making that relation happen, I don't know what that is, but it could be any kind of formula or like that. But my solution is my domain is going to be your whole first set of numbers. So it's whatever comes first. And frequently, this is what we're going to be calling our input, or sometimes we call it the independent variable. And frequently, it's going to be your X. The range is frequently called the second set of numbers or second set of variables or whatever it is we're looking for. And this is usually your output from something or your dependent variable. And it represents Y's frequently. What we see here is that with this relation, like I said, is a set of X's are related to Y's. The domain is all these first set of numbers. So your domain would just be the numbers 0, 1, 2, and 3. And then your range is this whole second set of numbers, or your Y's, which is 187 and 212 and 225 and 238. So just to recall here, when we're writing down a set like we did there, when numbers of when the elements are individual numbers in a set, we should not write numbers that repeat, and elements are going to be arranged in ascending order. So remember that as we go forward. So take a moment here and find the domains and ranges of these relations. So remember, if a number duplicates in your domain or your range, you only write it down one time. And you want to write those numbers in ascending order from smallest to largest. Okay, so for A, the domain, like I said, is all your first set of numbers or your X's. So my domain would end up being the 11, 12, 13, 14. So write them in order from smallest to largest. 11, 12, 13, 14. And then we close our roster set. So your range is all your second set of variables are all your Y's. So that'd be the 13, 18, 23, 28. Unfortunately, they already come in ascending order, so we just write them down the order that we give them. Now for B, we get a -2, -1, -1, and 3. That is my domain of the first numbers. So the smallest is a -2, then we have -1. We have it two times, but I only write it once in the set, and then we have the 3. So here the domain is only really three numbers. The range would be 4, 0, 2, and 3. Starting with the smallest, the range is going to be 0, 2, 3, and 4. So point out here, the relation is telling you what number is related to which one and how. When you write them down in your domain and range, we break that. We're just looking for what numbers go in the domain and what numbers go in the range. So we end up breaking the relationship there. So for C, my domain is 4, 6, 8, and 10. And my range is just one number. It's just 2. That can happen too sometimes. So a function is a special kind of correspondence between two sets, or a special kind of relation. The relation and correspondence get kind of used interchangeably. The first set is called the domain, and the second set is called the range. For any member of the domain, there is exactly one member of the range to which it corresponds. This kind of correspondence is called a function. So what we're seeing here is it's just this one direction that whatever's in the domain corresponds to exactly one thing in the range. That's all we should see there. Now, that doesn't mean that you can't have two different numbers in the domain go to the same number in the range, but what we have is that the domain should just only go to one number in the range. So if that sounds completely confusing, that's why we're going to have some images here to explain it a little better. So the function, note the bubble on the left of each one of these is a domain, and the bubble on the right is the range, and the arrow are the mappings. So we're going to write D and R for domain and range. But each one of these is representing a different kind of relation. And these two represent functions here. The first one is a one-to-one function. 1 goes in, it only goes to 3. 2 goes in, it only goes to 4. 3 goes in, it only goes to 5. 4 goes in, it only goes to 6. But what we see is that each element of the domain maps to only one element in the range. That's all we see here. We see the same thing here. This 1 only goes to 3. This 2 only goes to 4. This 3 only goes to that 5 in the range, and that 4 only goes to that 5 in the range. So even though they're both going the same number, this 3 only is mapping to that 5, and that 4 is only mapping to that 5. Like I said, each element of the domain maps to only one element in the range. They could all go to 5, and it would still be a function. What breaks it is situations like this. Here, we got the one-to-many. So it's different from the many-to-one. One-to-many, 1 goes to 3. Well, that's okay. 1 only goes to one element. 4, however, is going to two different elements. So in the relation on the left, element 4 in the domain maps to multiple elements in the range, which are the 2 and -2. So this is going to cause it to not be a function. Now over here, 1 goes to the 4, that's okay. 2 goes to the 4, that's okay. But this is the problem here. So this is the many-to-many. So the part that only breaks it is this part with the 3. We see a similar scenario with other relation, except with the 3 in the domain. We see that 3 mapped to a 5 and a 4. So this causes it to not be a function. None of these are functions because we have at least one element that maps to two different numbers in the range. So we want to determine whether the following are actually relations. So with A, we want to make a little diagram to the side here of our domain and range. My domain is 0, 3, 6, and 9, but my range is going to be 2, 6, 10, and 14. And what we see here is each element of the domain only maps to one element of the range. So this one is a function. Well, if we look at B now, domain and range, B has 1, 3, 6, and 8 in the domain, and my range is 2, 4, and 5. So 1 goes to 2, 3 goes to 4, goes to 5, 8 goes to 5. This one is still okay because each element of the domain only maps to one element of the range. This is still a function. So I think we're probably pretty sure now that 3 is going to be the one that's going to be the problem here. So the domain is -3, 1, and 5. My range is going to be 0, -4, and 4. We see this -3 goes to 0. That's okay. 1, however, goes to 2 different values. So this is the problem here, is that 1 goes to -4, but that 1 also goes to 4. And the 5 also goes to 1, which is also not a problem. It's this part right here. So this is not a function because at least the 1 in the domain maps to 2 values, -4 and 4 in the range. So take a moment in your worksheet and do the same thing. Walk through these 3 relations or correspondences and decide which ones are going to be functions and which ones are not. Okay. So we see here, well, 11 only goes to 13, 12 is only going to 18, 13 is only going to 24, and 14 is only going to 28. This is a function. Here I have a problem. -2 goes to 4, but -1 goes to 0 and 2. However, 3 only goes to 3, but it's this one part right here. Equals -1 mapped over to y equals 0, and it maps over to y equals 2. So it gives me 2 different things. So this one's not a function. So here we have 4 goes to 2, 6 goes to 2, 8 goes to 2, 10 goes to 2. Which that's actually not a problem. So everything's mapping to 2, but 4 only maps to 2, 6 only maps to 2, 8 only goes to 2, and 10 only goes to 2. So each element in my domain, all my x's, only map to just one y individually. So this is a function. So what I've heard a lot of students say to help them with this is that if your x duplicates, like we have here, -1, -1 for my x, when your x duplicates, in these cases, that is when we don't have a function. As equations. If an equation is solved for y and more than one value of y can be obtained for a given x, then the equation does not explicitly define y as a function of x. So as you take more courses, you'll get to this point where we talk about like this is explicitly defined. So explicitly defined means that I should put in one I should put in one x and only one y comes out. We'll also have implicitly defined functions, which are a little different. You expect these rules to eventually change at some point, and it's usually Calc 1. To determine whether the equation defines y as a function of x. So what we need to do, I mean to pick some sort of value for x and see what I get for y. So let's say, let's say x is 0. So if x is 0, what we'd see here is we'd get 0 squared plus y squared equals 1, which means I get y squared equals 1, which means y would have to equal plus or minus the square root of 1, which means y would have to be -1 or 1. So x equals 0 maps to y equals -1 and y equals 1. So it is not a function. So all I have to do is find one place where this happens where I could put in one value for x and x does not give me just one y value. That's when we know it's not going to be a function. So x squared plus y squared equals 1 is not a function. And if you want to know the graph for this, it's actually a unit circle. Here I have x squared plus y cubed equals 1. We'll do a similar thing. Well, what if x was equal to 0? What would y have to be? Well, let's see. If x equals 0, then I'm going to have 0 squared plus y cubed equals 1, which means I have y cubed equals 1. So that means the only thing that y can be, if we do a cube root of 1, is that y can only be 1. So in this case, and we could keep repeating this over and over again, if you do this indefinitely with different things, different x values, 0 is the easiest. What we're going to see here is this one is a function. One of the things to notice here is the y. X squared plus y squared equals 1. Not a function. I'm not saying this is the best way to do it, but this is a kind of a way to help you figure this out. So if your y has an even power, it's not going to be a function. If your y, however, has a odd power, you would get a function back. Okay, so we're going to determine whether the equation is defined y as a function of x. So as I said before, if the power of y is even anywhere, it is not a function. When that happens, that means you end up with two different y values every time you look at an x value. I'll give you a moment here. So just using that, the power of y, there's some important words missing in here. Let me fix that. So if the power of y is even anywhere, so if you have like two y's, but one of them has a positive on it, then you're not going to have a function. So hopefully you had a moment to go through that. So another way you can do this is not just look at that, but go, okay, if I get y by myself, here y is just equal to 5x minus 1 minus 3x squared. So y is explicitly defined. Y has a power of 1. So this is going to be a function. Here, if I isolate the y squared is equal to 1 minus 3x. So whatever I put in for x, I'm going to end up with two y values. So since the power of y is 2, which is an even number, that's pretty much not a function. It's an oversimplification of it, but it's working for us. Here, I can pull out a y. So if I factor out a y, I'm left with x plus 1 equals 2, which means that y is just going to be 2 over x plus 1. Whatever I put in for x should only give me one y now. So this is also going to be a function. Do some function notation. Given that x is an element of the domain and y is an element of the range, then y equals fx represents the functional relationship between the domain and the range. And it represents the functional relationship between the domain and the range as y is a function of x or fx is a function of x. So what we have here is that this gets a little confusing because this represents a function, but it also tells me that I can always replace y's with an f of x. So y equals f of x is the name of the function, and with x representing the input of the independent variable and y representing the output of the independent variable. Also, fx is the output. So get kind of comfortable with the fact that you can just replace y with f of x. Part of the reason we have this is like, if I had y equals 2x minus 7, but I also had y equals 2x squared minus 3x minus 1. These are two different functions. So what we like to do, so we can know which one's which, we're talking about our x's and our y's, y is always going to be dependent on x. So we're going to get different y's for x's. So what we would start doing is we just give them different names. So instead of calling this y equals 3x minus 7, we'd say fx equals 3x minus 7. So we've named the function. We might call this one then g of x equals 2x squared minus 3x minus 1. So it gives them different names, and it helps me, like figure out what's going on with multiple formulas going on. I don't ever talk about y's anymore. I just talk about f and g. So function names, we can give other names for a function of or other variables. So if we're working with multiple functions, we may have functions that we call f of x, g of x, h of x, q of x. There's a lot of things that we might use. Sometimes the name of the variables, a variable function, variables in the function tell us about a scenario that's being modeled. So velocity of an object given a time could be vt. V is representing that velocity is representing that time. This representing the independent of the input, and this whole thing representing the output. We also some functions can have special names. So one of the things that we're going to use is logarithms in this course. So this ln, this means natural log of x. This is a function I can't write out with a formula. Meaning I can't write something like this and have this formula go through this. So relationships that I can't write a algebraic formula for, we sometimes give special names to. So we'd have natural log of x, the sine of x, the arc sine of x. So sometimes you'll see these specialized names for functions. So function notation, the special notation fx, read f of x or f at x, represents the value of the function at the number x. So, what makes function notation complicated is the multi-use that we have of it. It's representing a function name, it's representing a y value, it's also going to represent a y value at a particular value for x. So it represents a lot of things. So what we mean is that if I have fx equals x squared minus 2x plus 7, and I want to evaluate f at -5, f at -5 means the output when the input, which is our x, equals -5. So if I have fx equals x squared minus 2x plus 7, you think that's where this x was? You kind of think of it like this empty space. But when I suddenly change and I say, I want to figure out what f -5 is, well, now that x, that empty space has been replaced with a -5. What that means is that every other place that I had an x is also now replaced with that same -5. So it's a way to evaluate the function at a given value. So this also means evaluate x squared minus 2x plus 7 when x is equal to -5. So that's why I say it's evaluate. Anyways, if I do figure that out, f of -5 is going to be -5 squared is going to be 25. -5 times 10 is going to, or so not times 5 is 10 plus 7. That is going to be 5, 6, 7, 8, 9, 2, 1, 2, 3, 42. So when x equals -5, the function equals 42. That is my output. Trying to get my red here. And then this is my input. All right, so take a moment and try to find each indicated function value. So we got a couple cases for you. So we got an f, a g, and then the same function again, a g, but we just changed what the input is. Okay, so for A, we want at -3 for f of p equal 5p minus 2p squared. So every place I had a p, I'm just going to leave that an empty spot now, just to help me out here. Now, what I'm seeing here is that I'm going to replace p with -3. So f at -3 means all my p's are now a -3. So I'm going to have 5 times -3, which is -15. I have -2 times -5 squared, which is going to be 9. I'm going to have -15 minus 18, or 8, 9, 10, 11, 12, 13, -33. Okay. There, got caught. There you go. So B and C, we'll just kind of do those together. So we got g of x. So I'm going to replace every place I have an x, I'm going to leave an empty spot. So it leaves me a blank here. So I have 3 of whatever x is minus 2, 3 times x minus 2, which we're leaving that blank, and then times x plus 2. I do this just to make it easier for myself. Like I said, every place that there was an x, I'm leaving blank. So all those places where I had an x, it's now a 2. I just stick in 2's in those places. So g of 2 will end up being 3 times 2 minus 1, which is 0, 2 plus 2, which is 4. So g of 2 is just going to equal 0. Okay. C is using the same function again, so using g. So g of x equals 3 times x minus 2 times x plus 2, except now we're replacing x with a 0. So we want to know what g is when x is 0. We'll have 3 times negative 2 times 2 now, which is going to be g of 0. It will end up equaling, I guess, negative 12. Love my mouse pad. We're never going to talk about graphs of functions. So we want to look at the graph of y equals negative 4x plus 1. So this is a function. So all we need to do is just pick a couple x values and figure out what y would be. So let's pick, try to think of something will fit on here. Let's start with negative 2. Negative 2 will definitely be on here. Negative 2, let's do 0 and positive 2. So if I do negative 2, what this is telling me is that this y here, that's some sort of function value. I can change this and just call this f of x. So what you're going to see here is that when we start talking about functions, is that we start replacing y with f of x. So I'm asking you to find f at negative 2, to find the y, and I'm asking you to find f at 0, and I'm asking you to find f at 2. So we know that the function is just negative 4x plus 1, so that is negative 4 times negative 2 plus 1, which is going to be 8 plus 1, so that one's going to equal 9. So the ordered pair, negative 2, 9. F at 0 is going to be negative 4 times 0 now plus 1, which is just going to be 1. And f of 2 is just going to be negative 4 times 2 plus 1, which is going to be negative 8 plus 1, or negative 7. Now to graph these, negative 2 and 9, 0 and 1, and 2 and negative 7. All right, hopefully I can make this tool work right. And there's the graph of my function. So hopefully you can start noticing something similar about graphs of functions. So number 5, just try it yourself. So now you have x plus 2y equals 6. So just find a way, what do we need to do to make it help graph this function? And we also have number 6 here to look at as well. Okay. So we have x plus 2y equals 6. So 2y equals x minus, or 6 minus x, which means that y is this equal to 6 minus x divided by 2. So we used fx. Let's make this a new function name. So this is a function that we're going to call g of x. G of x is 6 minus x divided by 2. Instead of having y here, we're just going to write g of x. So let's pick some things to put in here. Let's say x is 0. Or sorry, x is 0. X is 6. Let's use 0. And think of something else to use. Um, Not -6. We'll use 2. Let me put those in order. 0, 2, and I'm looking for my y. I'm actually asking for what is p of 0? Well, that's going to be 6 minus 0 over 2, or 6 over 2, which is just 3. X is 2. I want my y. That means I'm looking for g of 2. So that is 6 minus 2 over 2, or 4 over 2, which is just going to be 2. And when I'm looking for x equals 6 and I want my y, I'm really looking for g of 6 now, which is going to be 6 minus 6 over 2, or 0 over 2, or just 0. Backwards there. So we got 0, 3, we got 2, 2, and we got 6, 0. So this is also should just be a straight line. And now this one we do have written as f of x. So when we're looking for y's, we're really looking for, there we go. My tool is missing here. We're really looking for f of x. So we already have a list of x's to look at. So we need to figure out what f of 0 is, f of 1 is, f of -1, f of 2, and f of -2. Instead of writing these all out, I'm going to make these go a little faster for us. So we need 0 first. So if f is 0, we have 0 squared minus 1, so we end up with just the -1. If f is 1, then we'd end up with 1 squared minus 1, so 1 minus 1, that will be 0. If x is -2, or sorry, -1, that's -1 squared, which is 1. 1 minus 1 is 0. If x is 2, 2 squared is 4. 4 minus 1 is 3. And if we have -2 squared, that is also 4 minus 1, which is 3. So we have at 0, we get -1. At 1, we're at 0. At -1, we're at 0. At 2, we're at 3. And at -2, we're at 3. Oops, forgot to write this part. And there we go. So that is going to be the graph here. So now that we can graph functions, it's actually going to make it easier for us to determine if they actually are, if we can graph equations, it will help us determine if they actually are functions. So if it is possible for a vertical line to cross a graph more than once, then the graph is not the graph of a function. So for an example here is, this is This is a graph of x squared plus y squared equals 8. So we already talked about if your y is squared, you're probably not going to have a function. And we see here that red line, that is the circle. So if I look at, well, what happens when x is 1? What's my y value? Well, when x is 1, we get two potential y values. One of them is y is going to be either negative 2.828 or positive 2.828 approximately. So the issue we have here is that for each x value, or not each, but almost every x value, I end up with two y values because if I look at 0, I get a y value here and here. A typo here, it's not 8, it's 9, it's equals 9. I just realized that. Here at 3, we only get one y value, but it doesn't matter because at least in one other place, you put in an x value and you got two different y's. So my input is producing two different outputs. So it is not a function. We need to determine whether the following graphs are functions. All we have to do is just that vertical line test. So if I draw a vertical line here to this graph, we see that we cross it here, here, and here. So for whatever this x value is, we are going to end up with three different y values. So it's not a function. So because we have three values corresponding to one value. This function, I can draw an infinite amount of vertical lines through it. And what you're seeing, we'll pretend they're all vertical because they weren't all, we're going to see that every vertical line I draw only crosses the graph once. So this is a function. So every vertical line intercepts the graph only once. So this is the graph of a function. I don't think we have to do much for this one. So if I just do one vertical line here, we see it's going to end up, I have two y values. So not a function, two y values just correspond to one x value. Here, I think in that spot, I can do it 1, 2, 3, 4, 5 times I cross. One x values corresponding to five y values. So the graphs that are not functions, they still represent a relation. It's just they don't represent a function now. I've had people in the past tell me that I can't graph a function that looks like, or I can't graph something that looks like this. I could totally make these graphs. They're just not graphs of functions. You use your vertical line test and determine which one of these is a function or not. So I drew a vertical line through it, but you see here, it doesn't matter where I draw that vertical line. It only crosses once. This is a function. Here, all I just need one vertical line and we see that it crosses it two places. So one x value gives me two y values. This is not a function. Okay. So these are both polynomials, just one's a polynomial with an x squared and one's a polynomial with an x 1, 2, 3 cubed fourth. I think it's 4, 5, 5. Okay. We'll say it's a cube. I think they're both cubes. So one was like an x cubed and one's a y cubed kind of thing. So they're both polynomials, but one of them is a function and one of them is not. So you probably very quickly noticed that I could draw every vertical line I could think of, and I'm only going to cross once. So we get a function. Here, I just have to worry about doing it one time. So let's say if I picked -2, here we see that if x is -2, then I can end up with y is going to be um, about 1/4, 1/8. Hit about 3/8. Um, Here it's about, no, I think this is 5/8. And then this one here, it doesn't matter, it's something different. This is going to be -1, and then it also hit a y value. Down here at would be 3, -3/4. I think that's what this one is. I think this one's 3/4. I'm trying to eyeball it and guess, but what's important though is that for that one x value, we do get 3 distinct y values. So this is not a function. Uh, so take a moment and use the vertical line test. So be careful here because notice that when we have an open circle, right? An open circle means that we don't actually have a point there. That's an empty spot. A closed circle means there's a point there. So this is just one of the examples I wanted to show you. So just take a moment and try to decide which one you think is actually a function and which one is not. All right. So here, what we'd have is there's only one place that we have to worry about, and it's right at x equals 0. So the problem we have here is that here, there's no point here. This is an empty point. But this right here, there's an actual value here. It's not empty. That means when I draw this vertical line, it's not hitting anything here. So here, intercept. The vertical line doesn't intercept the graph of the function or supposed function. It intercepts graph. Here it's not empty, so vertical line intercept. Basically, at this point, it misses it. There's nothing there, but it hits something here. But it only intercepts one, which is okay because I don't want to intercept more than one. This is a function. X equals 0 only takes me to y equals -2. That's the only place it maps to. Down here's a little different. So let me fix that a little bit. I have a glitching problem here. We see here, we intercept here and here. So I'm intercepting here and here because both of those are, they're not empty points. There's something actually there. In this case, when x equals 0, here, well, y could be 0, and here, y is -2. So it has two different y values, so not a function. Okay, so going back to function notation, so the given function, given the function y equals f of x, we know that f of 2 represents the function value at x equals 2. So it's telling me what y equals. So I equals when x equals 2. So if f of 2 equals 7, this means that when x is 2, then y equals 7. So the notation fx equals 7 means that for some value of x, function value is 7 or y equals 7. So from above, what we'd see is that, oh, well, we know in this case here, because it tells me that if I'm looking for fx equals 7, I know that x is supposed to be 2. So it's telling you a relationship here. So essentially think of it as this case you are given y equals 7, but in this case you are given that x equals 2. So they're telling you two different things here. Let me blow up this graph just a little bit. I got a little fuzzy. So this is telling you the T cell count given, let me close that just a second there. The T cell count given years after being infected with HIV. We want to use the graph to figure out what is f of 5 and what is x when fx equals 100. So remember, this is actually telling you that x is 5. So you want to know what is y? So we go down here and we look. Well, these are my x's, right? This is x is 5. So when x is 5, this is where we hit the graph. And what we see here is that, well, in that case, y is going to be 400. So f of 5 is 400 cells per milliliter of blood. So it tells me that y is also going to be 400. Now, in this case, what this is telling me is that when I say fx equals 100, remember fx is just y, so that's just y equals 100. So we want to know, what is x? Well, y is now 100, so here are my y's, and right here is 100. So if we look at y equals 100, we go to the graph till we hit it, which is about here, and we go down. So what we get is that x would be 9 years. So what we know here is that f of 5 equals 400. So after 5 years, we should have a T cell count of 400. And f of 9 is equal to that 100. So after 9 years, our T cell count should be 100. I don't know how old this data is because got a lot of medication that changes us nowadays. Okay, so this is a different graph we have here. So this is age and your target heart rate again. So the following graph represents the age of an individual and their target heart rate. What is the target heart rate for a 46-year-old? And then we want to know if an individual has a heart rate of 110 beats per minute, what is their probable age? So that is, we'll find X, given that we now know that Y is 110. So here we want F of 46. So we know that X is 46. So we get close as we can to 46. It should be about here. So help me out. I'm going to use little arrows here. I hit about here on the graph, which means we hit about here. So 100, 110, 120, 130. That means f of x is going to be approximately 130 beats per minute. Okay, so here we have an individual heart rate, so we know what the Y is. We want to know what is the probable age. So we know that Y is 110. We want to figure out what X is. The Y is 110. Forget about here. So as long as you got close to this, it's about 75, if you count that. So Y is approximately 75. So F of 75 is going to be 110 beats per minute. Okay, I was like reading this. This is a target heart rate for exercise. So this is the heart rate we want them to be at. It's like going, their heart rate altogether should go up, but it's the target heart rate. The younger you are, we want to hit a higher target heart rate while exercising. So graphing, find the domain of a function from its graph. We look at all the inputs on the x-axis that correspond to points in the graph. To find the range of a function from its graph, we look at the output on the x-axis that correspond, or the y-axis that corresponds to points on the graph. So we have the little boxes here. So what we mean is if I have this function here, there's a blue line, and I want to know what the domain and range are. Well, the domain is just all my x values. So I look, okay, so my x values, I have an x value here. This corresponds to some sort of x value. This corresponds to some sort of x value. So each part on the line, there is an x value that goes with it. And what we see is that my x values in this case are extending from this -2 to 1. And if you remember with interval notation, it means that it's starting because we got close points at -2. So my x value is my domain. My smallest value for it is -2, and my largest value for it is 1. Or you can write this in interval notation, -2, 1. Now, when you talk about range, range is your y values. So look in the y-axis. So any point that I look on my graph, it corresponds, has some sort of corresponding y value to it. So we just want to know what all those values are. So we see that our smallest here for y, the smallest y value that we have is 0. And the largest that we have is 3. So y is between 0 and 3. Okay, so without little boxes on here, we want to use use the graph of the function to identify its domain and range. So keeping with the tradition that we had going, we'll do domain in blue. So remember, domain, that's going to be x values. So if I'm looking for my x values, we see all these points are telling me an x value. So from the -2 to the 1, I have some sort of x value because there's no breaks in the graph. However, remember that this is an open point, meaning that I don't actually have an x value at -2. I just have an x value really close to -2. So x has to be greater than this -2 and goes up to, but it can't include this 1 because it is closed there. So you might see your domain written like that. You might also see this x bar like this saying your domain. Or we might just say it's a parenthesis because we don't include that -2, 1 bracket because we include it for interval notation. And we talk about the range. Range is supposed to be y values. So with the range, we're looking at every possible y value that can be obtained according to this graph. And what we see is that we get everything between this 2 and this -1 down here. So we start with the smallest value first. So my smallest possible y value is this -2, and it is included because that's a close point. And my largest possible value is very, very close to 2, but not actually 2 because that's an open point. So we get really close to it. So the range of y is -1 is less than or equal to y, which is then less than 2. Or bracket -1 because the -1 is an included point, 2 parentheses because the 2 is an open point. So for the following, for the function f represented below, determine what is the domain range. Then we're going to do x and y intercepts 0, or f is 0 and fx is 0. So as a reminder, intercepts are when you intercept the x-axis, and y-intercepts when you intercept the y-axis. So our domain, in this case, we got arrows are going forever on my ends, which means when I'm looking for my x values, this keeps on going forever. So I keep hitting x values out here. So what that's telling me is that as far as my domain goes, I'm at the end going to -infinity because I'm getting smaller and smaller values of x. And this way, because I keep growing in this direction, I keep getting x values. This is going to positive infinity. So what we'd say that domain is, it just keeps going in both directions for infinity. The domain is, we could say, is all real numbers. Or we can say it goes from -infinity to infinity if we use interval notation. So I accidentally switched my colors, but my range is going to be blue this time. So range, let me get rid of all my little red lines here causing me problems. So we talk about range. Remember, this is still going indefinitely. So as we go up, we're still getting y values, right? They just keep on going. However, when we're looking at y values going down, we do hit a point. So it looks like here, my lowest y values are right here at -16. So my range would be -16 is where I start. And I stop at infinity. So remember, infinities are always open points because I can't actually reach them. All right, so x-intercepts. So every place I cross the x-axis, so those are going to be the points. Give myself a little more room here. Those are going to be the point here. So we have a point at -3, 0. We have a point at -1, 0. We have a point at 1, 0, and we have a point at 3, 0. So you might see it like that, or you might see them written as just x is equal to -3, -1, 1, and 3. So let's do over here, y-intercepts. Actually, I might be able to fit it in one here. The y-intercept is when we cross the y-axis. We only do it here at 9. So the y-intercept is y equals 9, or you might see it as 0, 9. So notice that x-intercepts, your y is always 0. Y-intercept, my x is 0. That's going to give you a hint to what I'm asking here in a second. So here, for C, we're asking for f of 0, which means x is equal to 0. So we would go up, x is equal to 0. So that means that y is going to be 9. So f of 0, no matter what the function is, f of 0 is always asking for a y-intercept. You notice that matches the y-intercept. So use pink here. If x equals 0, this means that y equals 0. So when y equals 0, or y equals 0, then my x values could be -3, -1, 1, or 3. Okay, because each x value is only mapping to that 1, so it's still a function. But in this case, if you're ever asked for f of x equals 0, this is going to be representing x-intercepts. Okay. So work on 9 here, find your domain and range. Don't worry about intercepts in this case. Find f of 2 and figure out when fx equals 3. Then do 10 and 11. So here you're asked domain and range, and then you're asked for those x and y intercepts again, and then a function value in both cases. So 9, 10, and 11, work on those, see if you can find those domains, ranges, x and y intercepts, and then your function values that you asked for. Okay, so there we go. Where's writing D and R for domain and range? For this function, my domain, so I always say you look for your smallest x value, which we see here. My smallest x value is -4, so this is marked for us. And my largest x value is going to be this 3. But we see that we hit everything in here. We have an x value all through here. There's no breaks. So my domain would be x is between, and those points are close points. So we would include the -4 and the 3. Now for the range, we want our smallest possible y value, which appears to be right here and right here, and that value appears to be 0. And we include that 0 because in either case, this is a close point, but we assume when it comes down and touches here that that's also a close point. We assume that all these points in here are closed. We actually hit something. My largest possible y value is here at 16, and that is also included as well. All right, let me get rid of my stuff on here. So now we want to figure out what f of 2 is. So that is when x is equal to 2. So when x is 2, we see that, and this is just a good guess, but it looks like y is 12. Then we're asked for fx equals 3, so that means x will be, so y is the 3, so if you see, that would be right here. So always be careful when you're trying to find y values. Sometimes you end up with 2 of them. So we're getting as close as we can. If I was to say what I think this is just a little bit before hitting that 3 down here on the x value. So you might guess that, and this is just a little bit before that 5, that 4, that -4. So maybe a -3.9, and here might be a 0.9. So just the closest x values we got there. So for 10, looking for domain. So we see that I'm looking for my x values. My smallest possible x value is the -5, but that's an open point, so I don't actually equal -5. And my largest is 4. And I do include that 4, so I would include it in here. So x is between, it's -5, which is less than x, which was less than or equal to 4. All right. I don't remember if I did this last time, but be careful with range. That is a y value. I'm trying to remember if I accidentally made a mistake earlier. So my lowest possible y value appears to be here at -2. And like we said, we assume that everything on this line is a closed point. So that means I would include that -2, so it actually equals it. And it looks like I max out my largest possible y value at 4. So we're not looking at the endpoints of the function, we're looking at where is my largest possible y value across this entire function. Where is my largest possible x value across this function? So x-intercept, it looks like we only have one here as an x-intercept. So that's like maybe a -0.9. Y-intercept, x is equal to -0.9. Y-intercept appears to be roughly here. Well, it looks like maybe like 1.5. That's at y equals 1.5. And we want f at -5. So here's -5. And as we see, that was an open point. There's actually not a value there. It's undefined. You say undefined. Yeah, we'll say undefined. I'm trying to think of if there's another way to say that. So we go through there. There's nothing there to define it. We just say we don't know. It's just open. There's nothing there. Fx equals -1 means we're trying to figure out what x is. So at -1, that's right here. So don't let this confuse you because it looks like it goes through this point and this point. Remember, this one's open. This is the only one that is closed. So when y is -1, my only x value is this -1.5. Okay, and the last bit here. So domain keeps on going forever in this direction. So when I'm looking at my domain, this keeps going this way, which means I keep getting y values. So my y values keep on going this way. They're getting more and more negative. So we're going from to -infinity. So as function or as interval notation, we'd say -infinity, and then we'd say, well, my maximum x value appears to be this 2. So if we were to write this as an interval notation, not interval notation, I'm sorry, as an inequality, then all we could say here is that all my x values have to be less than 2. So that's another way of writing that same domain. So my range, same thing. As I look at y values, because this is going this way, my y values keep on going toward -infinity as well. But my y values max out here at 8. And we include that 8 because that is a closed point. So we can write that, or we would end up saying, well, actually, all my y values are less than or equal to 8. And my x-intercepts, I intercept here, here, and here. So my x-intercepts are -2, 0, and 1. And my y-intercepts, This happens sometimes. So you have an x-intercept at 0. That also means that you will have a y-intercept at 0. So if you ever cross the point 0, 0, that is both an x-intercept and a y-intercept. So I'm just trying to catch all the things that you may potentially see or close to them. My last bit, f of 2, so x is 2. That's where x is 2. And we got that closed point there. So like last time, we didn't have a value. This time we do because that point is closed. So here we get y is 8. It's just telling me exactly this is a point that 2 and 8. It's telling me 2 and f of 2. Or in other words, 2 and 8. Fx equals 0. So that means x would have to be, that's that point right there. Well, x will also be 0.